Hello, future engineers. This is Madan Mohan, and remember, engineering is not just a subject, it's a passion, it's a mindset, it's a lifestyle. Today, we are going to see Poissons and Laplace equations. If charge exists, we use Poisson's equation. If no charge exists, it reduces to Laplace equation. Imagine a region in space. If charge is present inside it, its potential behaves in one way. If no charge is present, it behaves differently. These two cases give us Poisson and Laplace equations. Electromagnetic theory becomes powerful when we convert field concepts into solvable equations. Poisson's and Laplace equations allow us to compute potential in real engineering systems. So let's start Poisson's and Laplace equations. As you know from the point form of gas law, that is Maxwell's first equation, divergence of electrical flux density is equal to volume charge density rho v. From the definition of electrical flux density and the relation between D and E, we can write D is equal to epsilon E. So we know the relation between electrical field intensity and potential E bar is equal to minus del V. So we can write in place of E as minus del V. So del dot D is equal to divergence of, in place of D we can write it as epsilon E, which is equal to, in place of V we can write it as again minus del dot epsilon del V, which is equal to rho V. So in the left hand side we do have divergence of del V is equal to, we can take out epsilon to the right hand side, it is going to become minus rho V by epsilon, and hence del square V is equal to minus rho V by epsilon. So this equation is called Poisson's equations, but here the double del operator must be understood, and we have to expand at least for Cartesian coordinate system before the equation can be used for deriving other equations. So if you know del dot A is something like dou ax by dou x plus dou ay by dou y plus dou az by dou z. So in place of A we can replace it with V, potential dou V by dou x into ux plus dou V by dou y into uy plus dou V by dou z into uz. So now divergence of del V is something like dou by dou x of dou V by dou x plus dou by dou y of dou V by dou y plus dou by dou z of dou V by dou z. So it is going to be dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. Usually this operation del dot D is nothing but del square, so we can write del square V is equal to dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square. So in Cartesian coordinates we can say divergence square of V is equal to minus rho V by epsilon. As I said, if the value of rho V is equal to 0, which means that there is no charge existing, it indicates that volume charge density, and it is known that for a charge free surface space rho V becomes 0. Since there are no free charges in dielectrics, we can say del square V is equal to 0, nothing but Laplace equation. This del square operator of V is called Laplacian of V, and in Cartesian coordinates the Laplace equation is given by del square V is equal to dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square is equal to 0. That's all, my dear students, about Laplace and Poisson's equations. Thank you all. Bye.